Okay, we're now going to be using the Cartesian equation of a line. And this is something that we've known before, right? We're just the regular Cartesian plane with x and y coordinates, y equals mx plus b, point slope form, whatever form we kind of want. We want to know how to go back and forth from vector parametric form back into Cartesian form. So this first example, determine the equivalent vector and parametric equations of this line. So remember, for the vector equation, we have r, we have a point, and we have a directional vector. So the point's pretty easy. We have the y-intercept here, 0, 2, right? So I can just start by doing that, and I'll explain the rest in a sec. And then I have t with some sort of directional vector. So that directional vector is usually, that's why it's called vector m. So if the slope is 3 over 4, you can think of rise over run. I'll draw a little diagram over here. So from the origin, I go up 3 over 4, and this point is actually 4, 3. So that directional vector, 4, 3, you can pretty much come up with from your slope. So this is 4, 3. And this is the vector equation of that line. You want to come up with the parametric equations, no problem. X equals 0 plus 4t, and y equals 2 plus 3t. So I got the vector equation, I got the parametric equations, and I'm done. And I can put a little rule here. I'm going to say, so for vector m, that directional vector, if it's AB, it means that the slope is just B over A. And vice versa. If we know the slope is B over A, we can just say, well, that means the directional vector must be AB. So this rule will definitely come in handy to change slope into the directional vector to come up with our vector equations or parametric equations. Let's take a look at the opposite way. We want to go into slope y-intercept form. So we have a line with equation. Here's my vector equation, and we want to find that in slope-intercept form. So I'll do this in a few ways. So first of all, we know our slope is going to be negative 4 over negative 1, just based on this principle. So I'll actually do that in blue, and I'll do it on this side. So I know that the slope is going to be b over a, negative 4 over negative 1. So slope equals 4. Cool. So I'm halfway there. I mean, I have y equals mx plus b. Right now I got y equals 4x plus b. And now I need to plug in an x and y point to solve for b. So I can come up with that x and y point. There's a point right there. That's the only point I really have on this line. 3, negative 6. So this is negative 6. This is 4 times 3. 12, bring it over. This becomes negative 18 is b. And my equation is 4x minus 18. And I've switched it into this form. Now, there's other ways to do this. I could use the point slope form or slope formula. I can say y plus 6 equals 4x minus 3. Okay, this is just point slope form. It's the rearranging of the m equals, rise over run, right? If I just divide this down here, I have the 4, which is the slope, equals, the change in y over the change in x. And I can just solve for this, right? I can say y equals 4x minus 12, bring the 6 over, minus 6. Y equals 4x minus 18. And lastly, I'm just going to erase this for a sec. We know the slope now. I'm going to do one more form that you would definitely not know, and that's using the parametric equation. So I'm going to get parametric equations from here, and I'm going to say that this is 3 minus s, and this is negative 6 minus 4s. So what I'm going to do with the parametric equations is I'm going to solve for the actual parameter because I want to get rid of the parameter and have my equation in terms of x and y, just like I do here, solve for y, and that's slope-intercept form, really. So what I'm going to do is I'm going to solve for s, and I'm going to say s equals 3 minus x, and s over here equals y plus 6 over negative 4. Okay, I'm bringing the 4s over, bringing the y over. And the y is positive. Rearrange it, solve for positive s, and that's pretty much it. Okay, and I'm dividing by that negative 4. You can put the negative wherever you want. Now I'm going to set these two equal to each other. So 3 minus x equals y plus 6 over negative 4. I'm going to slowly keep rearranging. I can multiply this side by negative 4. So I'm going to get negative 12 plus 4x equals y plus 6. Bring the 6 over, negative 18 plus 4x equals y, and I've come up with the same equation using a third method. Okay, do you have to know all three? I mean, you don't have to do anything in math, but the more you know, the more versatile you'll be able to get out of problems that maybe you've never seen before. Okay, now let's talk about a little bit of standard form. Ax plus by plus c, everything on one side, 0 on the other. It's nice to know that the normal to this line, so let's talk about a normal. A normal is a perpendicular line. Okay, so anything that's normal is perpendicular. This marker is normal to this table right now. Okay, it is perpendicular. So if AB, the values in front of x and y, is the normal, we can come up with kind of our slope from the standard form. Perpendicular questions are easy, and also regular questions are easy, because if this is perpendicular, we can kind of understand based on the last screen what the perpendicular slope is to the perpendicular slope, which is just a regular slope. So we want to determine the Cartesian equation of the line passing through point A, which has normal 5, 3. So based on this principle, I already know that if this is the normal, 5 and 3 go in A and B. So I'm going to say, well, my equation must be 5x plus 3y plus c equals 0. And I want to find the Cartesian equation, right? So y equals mx plus b, Cartesian equation. Now, well, it's going through this point. The only thing I'm missing is c. That's pretty light work. I just got to do 5 times 4 plus 3 times negative 2 plus c is 0. 20 minus 6 plus c equals 0. 14 on this side is negative 14, and I'm done. Now I know that determine the Cartesian equation does not ask for y equals mx plus b, so I'm going to say, therefore, I got 5x plus 3y minus 14 equals 0 satisfies these conditions, and this is my answer. Okay, so now that we know that in standard form we can figure out normals easily and perpendicular slopes, we can come up with some statements here. So if lines L1 and L2 have normals N1 and N2, that's not a comma, that's a 1, then line 1 is parallel to line 2 if and only if their normals are scalar multiples. So if we know that their normals are scalar multiples, we know that these lines are parallel. So what's that mean? We can come up with a statement here and say, well, N1 must be equal to some sort of scalar multiple of N2. And that's what that means. Second, they are perpendicular. Line 1 is perpendicular to line 2 if and only if their dot product is 0. We know that as well. So the normals must have a dot product that is 0. Right? We know that these lines are perpendicular if their perpendicular lines are perpendicular. Yeah, of course, right? So this should be 0. So let's see an example here. We want to show that the lines L1 and L2 are parallel and non-coincident. Non-coincident means not the same line. They don't coincide with each other. My two hands are parallel and non-coincident. Now they're coincident, all right? So what we can do, we can say, well, let me look at this normal here. The normal here is 3, negative 4. So the normal for L1 is 3, negative 4. And the normal for 2 is 6, negative 8. These are scalar multiples of one another. I can represent this by removing a 2 and saying this is the same thing. Let's look here. If the normals are scalar multiples, they're parallel. The normals are scalar multiples. So I can say, therefore, since normals are scalar multiples, L1 is parallel to L2. Now, how do I know that they're not coincident? Well, I know if this normal is twice the size as this normal, this is the scalar multiple, let's check if it's the same line. Well, if I'm going to take negative 6 and multiply it by 2, I should get negative 12. I do not. I get positive 12. Therefore, they are not coincident. Okay, and that's pretty much it. That's how you figure out if they're coincident or not. You just, is the scalar multiple the exact same for the whole line? And we know that, equivalent equations, right? You can multiply an equation by anything. You're not changing the equation. It makes it coincident. So I can add here and non-coincident because the lines are not scalar multiples. The slopes are scalar multiples, the normals are scalar multiples, but the lines are not. Okay, so we're just gonna go through 2 more examples and we're done here. Okay, and last but not least, obviously we have to come up with a K question where we don't know one of the values, and we're gonna start talking about angles eventually too, because this has been a little bit too easy. So for what values of K are these 2 lines perpendicular? So on the previous screen, we learned, normals have to be perpendicular if the dot product equals 0. So for instance, I know that these 2 lines are perpendicular, so I'm gonna say L3 is perpendicular to L4 if N3 dot N4 equals 0. I can even say if and only if. So I can break that down and say, well, the normal for line 3 is K4. The normal for line 4 is 3, -2. Remember the A and B values, right? This must be equal to 0. Well, dot product's pretty easy. This is just 3K plus -8, so -8 equals 0. So K is 8/3. Pretty easy, right? But I gotta kind of remember that if I'm dealing with a perpendicular line, I can use the normals and their dot product to kind of figure out this answer. So it's not as straightforward in the grand scheme of things, because you gotta know all these little puzzle pieces and know when to apply them to create whatever puzzle you're creating. Okay, moving on, last question. I'm gonna throw in an angle just because it's the last question, and why not? Determine the acute angle formed at the point of intersection created by the following lines. So we wanna know this line, when they intersect, what is the acute angle? So if this is obtuse, we want that angle, whatever the acute angle is, okay, that they intersect. Now, these lines, wherever they are, the directional vectors are the only thing that matters because it's not going to change that angle at the point of intersection. The points in these vector equations is just going to move these lines around, but it's not going to change their direction, which means they're going to cross eventually at the exact same angle. So we don't care about the points. We only care about the directional vectors. Use the directional vectors. Okay, and I can use my formula for dot product, and I'm going to rearrange it and solve for theta because we have a cos in that formula. So I'm going to just come up with the cos formula. This is A dot B over the magnitude of A times the magnitude of B. So this is just a rearranged formula to solve for that angle in the formula for dot product. And now I can keep going. I can say, well, the cos of -1, the dot product, I'll break it down, dot 3/4 over the magnitude of A, that's just √10, and the magnitude of B is √25. Let's take it here. Dot product's pretty easy. -3 plus 12, so 9, over 5√10. That is false, sorry. Cos -1 of 9 over 5√10. Calculator that up, and I'm going to get 55.3 degrees. Done. Okay, pretty straightforward. Very important to understand that you only need directional vectors because that angle is never going to change. The directional vectors are the ones that tell us the slant, the slope, all those things that matter. If I was looking for the obtuse angle here, I'm just going to find the supplementary angle to 55.3 because if they're crossing, let's say it's like this is going to be obtuse, this is going to be acute. So if you're finding the acute angle and you want to find this guy, just do supplementary angles, 180 minus it, and vice versa. Okay, so don't let that little word acute angle scare you out of this question. And that's 8.2, done, easy.